In this video, we're going to take a quick look at logistic regression. So, first and foremost, we're going to read in some data. We're going to call this reg data today. And to take a quick peek at this data set, this is a health data set. Now, with logistic regression, we may be interested in a binary outcome. Now, oftentimes this will be coded such as 0 or 1. This is the best approach to use when we are doing logistic regression. And then we can see some other covariates in here that we may be interested in. So today we're going to consider the outcome of heart disease, and then we may consider some other covariates such as BMI. I'm going to pull in male rather than sex to make sure that we know which sex we're modeling, as well as cups of coffee, total cholesterol, systolic blood pressure, and age. So let's come back to our data set. Now, the function that we are going to use for logistic regression is not LM, which fits linear models, but GLM, which is going to fit a generalized linear model. And remember that if we are in R, we can do a question mark before the function name to see the manual page for it. So we're going to use this formula argument to set up, first and foremost, the items we're interested in. So just for a bit of reference for myself, I'm going to do head of reg data so that I can see the variables and the names of the variables. And so we can give this some name. I'm going to call this example log for our logistic regression. We're going to go GLM. And so I said I want to predict heart disease. And let's throw a few other variables in. So perhaps age and systolic blood pressure and total cholesterol and current smoking status could be an interesting one. BMI, and we'll stop with coffee in this case. We'll leave out our obesity and diabetes flags. Now, as with other regression items and using formula, I need to specify the data set that this is coming from. Now, there's one big additional item that we need for logistic regression. You can see this second argument here says family equals Gaussian. Now, that is not the approach that we need for logistic regression. We actually need to change this. For logistic regression, we are modeling a binary, or we can think a binomial output. Now, you can do binomial with parentheses or binomial without parentheses. This model will fit the same way. And these are the items that we need for what we're going to look at. Yes, there are some other options you can do, but we're not going to focus on those right now. So once we fit this model, we can come in and take a look at the summary. And summary is going to spit out a lot of items similar to what we see for ordinary linear regression, though we do see a few things that are changed. One, there's no residuals item up here at the top, but we do get coefficients with estimates, standard errors. Now we're using a z-value rather than a t-value, and then our final column is going to be a p-value. Down at the bottom, you may notice that some of the other outputs that we get from linear regression are not here, and then there's this new item, number of Fisher scoring iterations. This is because logistic regression does not have a closed formula, but rather does an iterative process. Now, very quickly, this is how we can get logistic regression in our outputs, but do remember when we are doing logistic regression, we are fitting the log odds of an event happening, in this case, of an individual having heart disease. Now, this can be nice in our initial interpretation of our estimates because we can come in and every value that is positive is going to increase, we often say risk, of the outcome, and if there were any negative, we would say that those decrease. So, taking a look at these values in here, and I realize I forgot male, which I said I was going to include, but we'll consider this model as it is. We can see that ignoring significance at this point, we may just say that an increase in age, blood pressure, cholesterol, somebody that smokes, higher BMI, and increased drinking of coffee all have an increase to the risk of heart disease. That's because all of these values here are positive. Now, interpreting exactly what these values are and trying to put in coefficients to get a prediction is going to be very difficult. Recall we have special formulas we use for our predictive probabilities, and what we tend to look at far more often than just these estimates is we will often want the odds ratio, because odds ratios are going to tell us the difference comparative between two groups, but this difference, well, on the log scale, once we multiply things or exponentiate to get back to just the odds, are actually going to be ratios. And so, for example, to get off of the log scale, I'm going to do exp for exponential, and you can type these numbers in directly to exponentiate them that way, or perhaps, in this case, you can, if you want to pull the values out exactly, you can do the name of the fitted object. We're going to grab coefficients. Now, coefficients is going to be this entire matrix here. I don't want the entire matrix. Perhaps I want just the odds ratio for current smokers. So in that case, I need to grab the 1, 2, 3, 4, 5th row and first column. And if I do this, now, apparently I grabbed the wrong values there. I probably have misnamed this. So we will, I remember now. We need to add summary in front of this. And now I can add coefficients. And so now we have 0.35241 exponentiated, and so we could say that there is an odds ratio of 1.48, meaning that those that are current smokers have odds that are 1.48 times those that are not current smokers. So these are some brief things we can do with logistic regression. Primarily how to fit the model, and then how to exponentiate back to get to our odds ratios.